I want to take a break from that kind of heavy, mathy, Maxwell type discussion and take a brief interlude to come back to the first question we asked, which is how does an antenna work? So I've told you if you nudge a charge, it radiates, but how does a real-life actual antenna work? How does it nudge those charges? Okay, so again, we said that nudging one electron is going to give you radiation, but in a real material, in real life, you don't often have just one single electron sitting around by itself. They tend to come with other stuff. So like in a copper wire, there's copper nuclei that are positively charged and electrons that are bound to them. So how does a real antenna work? Well, first what you do is you take your chunk of metal, you attach it to a little like battery or voltage source, and first the battery applies an electric field that makes the charges want to move. So it makes all the electrons in the wire want to move to one end. So all the electrons pile up over here. This object that we have now with all the positive charges bunched up over here and the negative charges bunched up over here, this is called a dipole. So this is an electric dipole. It roughly looks like this. The positive charges are bunched up here, the negative charges are bunched up here, and it has some electric field lines that point away from the positive charge and toward the negative charge. Okay, that's great, but this thing alone is not going to get us to radiate because we know we need charges to get nudged, right? You have to move the charges. So next, we reverse the dipole. This battery flips, and now it makes all the electrons want to pile up on the other side. Before they were on the right, now the electrons pile up on the left. So the electrons all move over here like musical chairs to get back over to the left. And that doesn't happen all at once. They're going to gradually move from one side to the other. You can imagine a little animation where the electrons are all over here, then they're moving and they're all over here, and then they come back and they're all over here. So it's kind of like a smooth, continuous bunch of nudges, right? You're nudging the electrons at each step, but they nudge from left to right, then right to left, and back and forth. So it's a nice, smooth nudging. And the point is that as you do those many small nudges back and forth, this is going to give you a smooth, continuous signal that kind of goes out and updates the electric field to where the charges are at a particular point. Excuse me. So I'll show you some animations. Here's one. The blue is the negative side, so you can see the electrons keep switching back and forth from top to bottom. As they do, the signal keeps moving out to try to update the electric field to the current locations of the electrons, but it has to keep going because the electrons never stop. So since they keep moving, you have to keep updating, and it keeps sending out these kind of pretty, keeps like shedding these like little circular loops of electric field, if you like, which are very pretty. And that produces a signal. So these are little arrows, these are vectors, but they carry some energy. So in this plot, I'll show you just the energy. This is an animation of the energy being carried outward. Energy is described by something called the pointing vector, S. So these two black dots in the middle are kind of the clusters of positive and negative charge, and as they dance back and forth up and down, it sends out this energy, which is shown by the intensity of the color. So the brighter color is more energetic. So you can see the energy gets weaker and weaker as you go away. But that's how real-life antennas work and how they send music to your car from a radio station. Okay, good. So that's a little more down to earth and some nice pictures rather than some heavy equations. So next, I want to move from antennas to the nature of space and time.